Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be talking about that ever important but all too often forgotten part of a titration, the chemical indicator. So whenever you're performing a titration, it turns out that most of the time we're not exactly concerned with the pH at every point in the titration. Usually we're only ever concerned about one single point in the titration, and that's essentially that equivalence point. And one of the reasons why is this is going to be that a very important point where the moles of analyte and the moles of titrant are equal, whether or not you're doing an acid-base titration or redox titration or something else. The very important part about these titrations is that the single point moles of analyte and moles of titrant are going to be equivalent. So if I'm looking at a weak acid strong base titration, this means that the moles of acid that I initially put in my analyte and the moles of sodium hydroxide that I added from my burette should end up being equal. And usually one of these values can easily be determined. So if it's your weak acid, usually you'll know the molecular weight of your weak acid and the mass you put in there. And ta-da, you have moles. If it's your sodium hydroxide, usually you've already determined the molarity of your sodium hydroxide, and by knowing the volume, ta-da, you know the moles. And as soon as you know one, you know both for that titration. However, this does end up relying on the fact that you end up nailing the equivalence point, because at any other point in the titration, this is not necessarily true. So what we have to do is make use of some special feature of the equivalence point. And what we end up taking advantage of is the fact that the pH changes fairly rapidly around the equivalence point. No matter really what type of titration I'm doing, weak acid, strong acid, weak base, usually we tend to see pretty good pH changes around that equivalence point. And so one of the ways we can try and identify this point is, instead of using a pH probe where I get the whole curve, I'm going to go ahead and use some sort of chemical indicator that should turn color around this point. So one of the big tricks is trying to identify some pH region that, as I go through it, I'll go from one color to the other, and it goes through fairly quickly. So for example, in your traditional acetic acid titrations or phenolphthalein titration or KHP titrations, it turns out that the range that phenolphthalein occupies, in between 8 and 10, is all near that equivalence point rapid pH change. Other indicators like methyl red would be very bad indicators, because it turns out that that encompasses most of your buffer region. So you end up changing color before you even get to your pH even reaches your pK, and it stays there for a long time. It has no relationship to your equivalence point. One of the other features that we often want is for our indicator to remain constant at all other colors, all other ranges. So for example, if I'm doing a classic KHP titration, it turns out that my phenolphthalein stays clear the entire time, because my entire titrant is below that 8 region, and I only have the one color change in that fairly narrow pH range of 8 to 10, just 2 pH units. And once I've gotten to the other side of my equivalence point, it stays red pretty much the entire time. So it lines up with my titration very nicely. So this kind of begs the question of, how do indicators actually work? How do they know when what the pH is? And this actually plays an important role in choosing the correct indicator, because it turns out that almost all of our indicators are going to be weak acid base conjugate pairs. So they're either going to turn colors when they're all protonated or deprotonated. So let's go ahead and take a look at the great example of phenolphthalein. So at low pHs, it turns out that phenolphthalein is entirely clear. It goes ahead and it forms this really kind of fun complex. And we have a nice conjugated aromatic ring here, here, and here, and there's no connection in between them. However, it turns out that under high pHs, if I've got a lot of hydroxide, I can go ahead and pull a proton off of this hydrogen, off of these hydrogens. That doesn't seem like it's will play a big role, but that causes the whole system to essentially rearrange and kicks off this and ends up breaking this bond. And so you end up generating this entirely different looking species. However, they only differ by essentially a proton. And what's very notable part is at this point, all three of these aromatic rings are all now linked in a big conjugated system. It means the electrons can move around very readily. And if you remember back to last semester with particle in a box, the bigger my box is, the more the electrons can move around, the closer my energy levels get. And this means that now I end up with a gap in between my molecular orbitals that can actually absorb a single photon in the visible spectrum, so that I now go from clear to pink. And most of your indicators have a very similar nature. One of the species has a lot of conjugation and one doesn't. Whether it's the deprotonated or the protonated species really depends upon the identity of your indicator. However, because each of these indicators tend to be weak acid-base pairs, it means that when you're in this pH range near the pKa, so plus or minus 1, you're going to have a mixture of both species, which means you have a mixture of both colors. If you're more than 1 pH unit below the pKa, you're just in the acidic form, in this case, clear. If you're pH of more than 1 pKa unit above, you're entirely the other species, in this case, a bright fuchsia pink. And one of the things that makes phenolphthalein such a good indicator is it goes from clear to, as soon as you even have a little bit of this conjugate base present, you're immediately some form of pink. And so one of the big features that you're using within all of these indicators is that under acidic conditions, so below that pKa, you're always going to be the color of your conjugate acid. And at pHs above your pKa, you're going to be the conjugate base, where sometimes, depending on the indicator, there may be a mixed color. Now, one of the important points to note is that the color change may not always occur at the end point, at the equivalence point. So we have to use a slightly different terminology to talk about when this color change occurs. And the phrase we use is calling it the end point, traditionally because when this color change occurs, that's when we know how to end the titration. And one of the important features you have to do is make sure that you line up when that color change occurs as closely as possible to the pH of the equivalence point. That way you can guarantee that the volume it takes to get to the end point is very similar to the end point where that color change occurs is very similar to the volume it takes to get to the equivalence point. The closer those two values are, the more accurate your titration becomes. However, it is worth noting that there are many different possible indicator choices, and depending on your choice of weak acid and weak base that you're trying to analyze, it can be very different sort of indicator. So this goes anywhere from indicators such as methyl violet, which have a nice pH, which turn color in between a pH of 0 and 2, as they go from yellow to violet. If you have your endpoint near a pH of 0, this is a great indicator. Turns out many weak acids have a color change near that pH of 7 to 9, at which point phenolphthalein is a fantastic choice of indicator. However, as we go through, especially working through looking at many different polyprotic acids, we're going to find sometimes where you're going to want a pKa closer to 5, at which point bromocresol green is going to be a good choice. But making sure that you know exactly when the pH of your equivalence point is going to be very important in trying to pick the right indicator. So this is one of the reasons why we spend a lot of time trying to find the pH of your equivalence point and your buffer region to make sure your buffer region is as far away as possible from this indicator and your end equivalence point lines up as good as possible. The other major choice when choosing an indicator is we want to make sure that that color change is easy to observe. So for example, when we use phenolphthalein, it's often because we're starting acidic when we have a nice colorless solution, and we end when the system is basic, where it's now pink or red. If, however, you are doing a strong acid titration, phenolphthalein is a very bad choice because it's much harder to see when a solution stops becoming pink than when it starts. So going red to clear isn't nearly as good of a choice. And so you're going to find many cases where the choice of what color change you're trying to observe could determine which indicator you want. For example, chlorophenol red goes from yellow to red. So if you're making the system more basic, that will be easy to see where the system goes orange or red. However, if you're adding a strong acid, this will be a little bit harder to observe as it'll be hard to see when the system goes yellow. However, using phenyl methyl red would be a much better choice, as going from yellow to red will be a lot easier to observe. So again, you can see which direction might be a little easier to observe the endpoints. So making sure you choose the right indicator is a lot about knowing what your titration should look like and what color pattern will be easier to observe, yellow to purple or purple to yellow. So next time, we're going to go ahead and look at a little bit more complicated systems as we try and talk about, return to talking about polyprotic systems and trying to figure out what form, what protonational state a molecule should be at any given pH. Until then, take care.